Hello class, thank you for joining me. Today we're going to be talking about chemical bonding and molecular structure. Now, before we get into that, we need to do a quick review of our knowledge of atoms. So if you recall, atoms are the smallest unit of an element that has all the properties of that element. And they don't change their identities in chemical reactions. Chemical reactions simply rearrange how atoms are joined together. These atoms are composed of three types of particles. They're called protons, neutrons, and electrons. And as we can see right here, the protons and neutrons are going to be joined together in what we call the nucleus, right? With our electrons orbiting the nucleus. Now, atoms can lose or gain electrons in the course of a chemical reaction, and they become charged particles, which we call ions. Cations have that positive charge, whereas anions will have that negative charge. So these ions are formed when neutral atoms are a net charge of 0 lose or gain electrons. And so the charge of an ion is determined by its number of protons minus its number of electrons. And so a neutral atom is going to have an equal number of protons and neutrons. So an atom that loses an electron will have an overall positive charge, whereas an atom that gains an electron will have an overall negative charge. Now, introducing molecules. A molecule is a combination of atoms that join together to act as a single particle. Right? So what I have here are two hydrogen atoms that are joined together, bonded together. Right? As you can see, there's two separate atoms, yet they act as one particle. This is a molecule. Right? And so if the atoms in a molecule are the same substance, we refer to it still as an element. If the atoms that form a molecule, however, are different elements, two or more different elements, the substance is then referred to as a molecular compound. And so for an example of that, we can consider water, right? We have two hydrogen atoms and one oxygen atom. So two types of atoms are in this one molecule. And so this will be referred to as a molecular compound. Now, the simplest molecules are diatomic. That means they're composed of two atoms. Some examples of this are hydrogen, oxygen, and nitrogen. Now, diatomic molecules can also exist as compounds. An example of this would be carbon monoxide, CO, and hydrogen chloride, HCl. Now, if you notice, there's still two atoms in each, or these two atoms are different. So both cases are diatomic molecules. Now, most molecules are not that simple. Most are more complicated. So again, we're going to look at the example of water. We take our hydrogen and oxygen, both which exist as diatomic molecules. We combine them, one atom of oxygen with two atoms of hydrogen to form a molecule of water. Right? We can see that demonstrated in the pictures at the bottom of the screen. We have our single hydrogen atoms and our single oxygen atoms, our diatomic hydrogen and our diatomic oxygen, and our water molecules, where we've now taken one oxygen and two hydrogens to form that molecular compound. Now, molecular compounds are typically going to consist of a combination of non-metallic elements. If you think back to your understanding of the periodic table, our non-metallic elements are going to be everything that's to the right of this line right here, whereas metallic elements are going to be everything to the left, minus hydrogen. Hydrogen is a non-metallic element. Now another compound to consider are ionic compounds. If you think back to our knowledge of atoms, we know that atoms can form cations and anions. So ionic compounds are simply cations and anions that have joined together. These compounds are held together by these electrostatic forces. It's this positive and negative interacting together. And the structures of these compounds are going to try and maximize attraction and minimize repulsion, meaning that positive is going to look for negative, negative is going to look for positive, and try to avoid the same forces. Ionic compounds are generally going to consist of a combination of metals with nonmetals. Again, thinking back to your knowledge of the periodic table, nonmetals being everything to the right of the step ladder, metals being everything to the left. All ionic compounds are going to have an overall electrically neutral charge, meaning an overall charge of 0. A good example of this is common table salt, sodium chloride or NaCl, where Sodium has a positive charge, chlorine has that negative charge. And so when you have sodium chloride, what happens is the positive charge of sodium satisfies the negative charge of chlorine and vice versa. Now, a question you may have at this point is, how do we determine what charge an atom has? To do this, we look at this table down here. By examining the columns of the periodic table, we can see a pattern emerge for most of the elements, right? So for group 1A, we can see that these atoms all have a positive 1 charge. Moving to group 2A, we see these atoms all have a positive 2 charge. 3A, positive 3 charge. Then looking at 7A, negative 1 charge, 6A, negative 2 charge, and 5A, negative 3 charge. Now, one thing to note is that hydrogen can have both positive charge and a negative charge. It is unique in that sense. So how do we write these formulas down? How would we show this on a piece of paper? We do this through molecular and empirical formulas. So molecular formulas are just abbreviated descriptions of a molecule where the types and numbers of atoms are shown. So what do I mean by that? If we take hydrogen, for example, H2, this is how we denote molecular hydrogen, right? We know it's hydrogen by H, and we know that it's diatomic with the 2. What about something a little bit more complex, such as water, right? We know that water is 2 hydrogen atoms and 1 oxygen atom. And so we denote this by saying hydrogen with an H, with a subscript of 2, and oxygen with an O, and an understood value of 1. Ionic compounds are a little bit different. With ionic compounds, we have to use empirical formulas. And the reason for this is if you look at this example of sodium chloride, it's a bit complex. We can see that there's an equal number of sodium and chlorine atoms, and that no one sodium ion is uniquely combined with a chlorine atom. So if we look at this sodium ion right here, we can see that it's interacting with 1, 2, 3, 4 different chlorine ions, right? And not any one uniquely. So, in order to write this, we're going to use the empirical formula. And so an empirical formula gives the relative number of atoms with the smallest whole number possible subscript. So for sodium chloride, that would be NaCl. So what do I mean when I say the relative number of atoms with the smallest whole number possible subscript? For example, we can see that for every 1 sodium ion, there's exactly 1 chlorine ion. So it's a ratio of 1 to 1. We have a 1 to 1 ratio where the smallest possible whole number is 1. So we have understood values of 1 here. So why don't we practice this? So starting off, we're going to write the molecular formula of the following substances. Diatomic nitrogen. We know that our element's going to be nitrogen. And thinking back to our earlier vocabulary, we know it's going to be diatomic, meaning 2. So this one is simply going to be N2. Alright, what about sulfur dioxide? So I give you a sulfur dioxide is 1 sulfur and 2 oxygen atoms. So we know we have 1 sulfur and 2 oxygen, SO2 for sulfur dioxide. Now we have something a little bit different in picture, right? Look at the picture, we can see that we have nitrogen and hydrogen atoms. And so we count 1, 2 nitrogen atoms, and 1, 2, 3, 4 hydrogen atoms. So we write this one as N2H4. Okay, so what about ionic compounds? Now let's practice empirical formulas. So the first one we have is calcium and bromine. How are we going to write this? Well, in order to do that, we refer once again to the periodic table. And we can see that calcium has a charge of 2+, whereas bromine has a charge of -1. Now in order to satisfy these charges, we're going to have to balance it out, because a 2+ charge does not satisfy a -1 charge. And so, in order to have that overall neutral ionic compound, we have to do C, A, B, R, 2. So the 2 bromines provides overall 2- charge, calcium provides the plus charge, giving an overall neutral charge. What about magnesium cations and sulfur anions? Again, look at the periodic table. We see that magnesium has a charge of 2+, and sulfur has a charge of 2-, meaning that 1 magnesium and 1 sulfur will give an overall neutral charge. So this one will simply be Mgs. And then lastly, potassium cations with oxygen anions. Looking at potassium, we can see that potassium has an overall charge of +1. Oxygen has an overall charge of -2. So, in order to satisfy the +1 charge of magnesium, the -2 charge of oxygen, we're going to need 2 potassium atoms for every 1 oxygen atom, so K2O, in order to have an overall neutral ion. So, should you want more practice, you can go and use PhET's simulations. Follow this link right here. And they have 2 different simulations, build a molecule, build an atom, both of which are really good tools to help understand what we just learned today and give you hands-on experience working with it. Thank you for joining me. Have a good rest of the day.